In 1907, a young engineer noticed that steel beams on a massive bridge under construction near Quebec City were bending, not according to plan, but under a growing, unexplained strain. He tried to get the project stopped. Before his warning could take effect, the bridge tore itself apart, falling into the river in about 15 seconds. It would collapse a second time 9 years later before it was ever finished. By the late 1800s, Quebec City needed a rail bridge across the St. Lawrence River, a waterway wide, deep, and choked with ice for much of the year, which ruled out a conventional bridge with many support piers. Engineers settled on an extraordinarily ambitious design, a cantilever bridge with a central span of 1,800 feet, which would make it the longest cantilever span in the world, a record it still holds today. The project's chief consulting engineer was Theodore Cooper, a respected and experienced figure in American bridge engineering. But the project was underfunded from early on, and Cooper, citing his own health, chose not to supervise construction on site, instead relying on a young inspecting engineer named Norman McClure to monitor the work and report back. Construction proceeded through the early 1900s, employing hundreds of workers, including many skilled Mohawk ironworkers from the Kanawake community near Montreal, ironwork that Mohawk crews from Kanawake had become particularly renowned for on major bridge projects throughout this era. Here's where the 1907 failure took root. Cooper had approved unusually high allowable stress limits for the bridge's steel, in part to reduce the amount of material needed and control costs on an already financially strained project. When later engineers recalculated the bridge's true deadweight partway through construction, they found the structure was significantly heavier than originally estimated. But rather than substantially redesigning the bridge to compensate, the project moved forward largely unchanged. By the summer of 1907, McClure began noticing a real problem. Several of the bridge's massive compression cords, the horizontal structural members carrying the load closest to the piers, were visibly bent. He reported this to Cooper. The bends grew larger over the following weeks. On August 27th, McClure measured the deflection again and found it had increased further. He immediately reported this to Cooper, who wired the construction company stop placing any more load on the bridge until this was fully understood. That warning arrived too late. On August 29, 1907, McClure traveled to New York to report his concerns to Cooper in person. Cooper, finally recognizing the severity of the problem, told him to send an immediate telegram ordering all work stopped and sent him onward to personally deliver the message to the construction company in Pennsylvania. The telegram was sent just after noon. It didn't arrive and reach the right people in time. McClure himself was still traveling. At around 5:30 that evening, before the stop work order could take effect, the weakened compression cords buckled under the load. The failure cascaded almost instantly. Witnesses described the entire southern span tearing loose and falling into the St. Lawrence River in roughly 15 seconds, with a sound purportedly heard for miles. 75 workers were killed. Only 11 of the men on the span at the time survived. Among the dead were 33 Mohawk ironworkers from Kanawake, a devastating loss concentrated in a single small community, one that profoundly affected the town for a generation. A Royal Commission of Inquiry placed the blame for the 1907 collapse squarely on inadequate design and insufficient checking, and construction resumed years later on an entirely new, much heavier design, this time under significantly more careful engineering review. By 1916, the new central span,
a single section weighing over 5,000 tons, was ready to be lifted into its final position using massive hydraulic jacks floated into place on barges below. On September 11, 1916, with government officials, engineers and photographers on hand to witness what should have been a triumphant final step, a steel casting in the lifting apparatus broke during the lift. The corner of the span dropped suddenly, and the entire section tore loose and fell into the river. 13 workers were killed this time, with several more injured. Unlike the 1907 collapse, this failure wasn't traced to a fundamental design flaw in the bridge itself, but to a single mechanical component in the temporary lifting equipment that failed under load.
The 1907 collapse remains one of the most studied engineering failures in history, specifically because of how avoidable it was. The Royal Commission found the core cause was defective design of the compression cords, compounded by Cooper's decision not to require independent recalculation once the bridge's true weight was better understood, and by a chief engineer on site who continued work despite mounting warning signs. The 1916 failure was a different kind of lesson, proof that even careful, well-supervised engineering can still be undone by a single failed component under extreme load, a reminder that redundancy and margin of safety matter at every stage of a project, not just in the original design. Together, these two failures reshaped how the engineering profession thought about responsibility itself. The disaster is directly credited with pushing forward the formation of professional engineering oversight bodies in North America, and it remains part of the origin story behind the Canadian tradition of engineering graduates wearing an iron ring, a lasting symbol of the profession's obligation to prevent failures like this one. The Quebec Bridge finally opened for rail traffic in 1917 and officially in 1919, nearly 2 decades after construction first began, and at a cost of 88 workers' lives across both collapses. It still stands today, carrying rail, road, and pedestrian traffic across the St. Lawrence River, and its central span remains the longest cantilever span ever built. It's recognized today as both a National Historic Site and an International Historic Civil Engineering Landmark, a rare case in this series where the finished structure itself became a lasting monument to the lessons its own failures taught the entire profession.